Hey everyone, how's it going? Terry Brown, Mechanical Engineering here to go through another engineering mechanics problem. This time we're going to have a look at a truss and we're going to solve it both by method of joints and then by method of sections. All right, so let's have a look at the problem. All right, so here it is. We have a truss, as we can see there, pin connected at E, roller connection at A, and some loads here. 7 truss members there to solve for. So we're looking for determining the reactions at the supports, the force in each truss member, and then once we've found the force in each truss member, to then indicate whether the member is in tension, compression, or it's a zero force member. Okay, so let's have a look at our solution. So as I said, we'll use the method of joints first, and then we'll check our answers with the method of sections. Normally what I do when I'm working on a truss problem is to draw the free body diagram of the entire truss first, and then work out the reactions at the supports, even if they're not asked in the textbook question. I'd like to always try and think about these problems from a design perspective rather than just from a solve a question in a quiz or exam perspective. So, if we really did have to analyze and design this truss, we would of course need to know the reactions at the supports, right, as well as the forces in all of the members and joints, not just one or two of them that may have been asked for in the question. Okay, and it's also good exercise to go back and revise your rigid body equilibrium. And it also, as we'll see at the end, provides a good check of our method of joints and or sections that we've used. All right, so there's my free body diagram, and now I need to just start adding in at the supports the reactions. So at A here, we've got a roller support, so it's free to move up and down here at this support, but constrained in the horizontal direction. So therefore, we'll have a horizontal reaction on our free body diagram, and we just need to put a sense, so put an arrowhead on that force, and you can just make an assumption about the direction or the sense it's going to be, or you can look at the problem and think through the equilibrium equations and try and work it out. So if we imagine that we take moments about point E here, our two loads are going to tend to cause this truss to rotate anti-clockwise. So therefore, for this truss to be in equilibrium, we need the force down here at A to be pushing to the right to tend to rotate the truss anti-clockwise. Right, so we can put that arrowhead in, give it a label that we can use in our equations. As you've seen, I tend to use RA or R or F subscript a letter to denote the point where the force is applied, rather than just using A and then up here we'll have horizontal and vertical components. So rather than just using EX and EY here, I prefer to label them with labels that indicate that they're a force. All right, so up here we've got our pin connection at E, so therefore a vertical and horizontal reaction. As I said before, they don't have to be vertical and horizontal. You can put them in any orthogonal orientation that you like, but usually the most convenient and easiest is to have them horizontal and vertical. So we can start thinking through whether they will be to the left or to the right for the horizontal one. So pretty easy in this case. The only other force acting in the horizontal direction is our force down here, RA. So assuming we've got that correct, then the horizontal reaction up here at E must be to the left. And then for our vertical one, we've got the only other vertical forces are the two loads. So therefore this must be acting upwards for that to be in equilibrium. Give them some labels, REX, REY, that we can use in our equations of equilibrium. Normally we would start with moment equation, and that's what I've done here to take moments about E, because usually that's what enables us to find one of our unknowns straight away. In this case, we could find REY straight away by looking at some of the forces in the vertical direction. So hopefully you can see that's going to be 5. If I take moments about point E, these two unknowns don't appear in my equilibrium equation, and I'm left with an unknown, or a single unknown, which will be RA here, which you can see already in my equation. So the moment of RA about point E is force times its perpendicular distance, which in this case is 1.5, and that's tending to rotate in an anti-clockwise direction about point E. So that's a positive moment. Then we have our 3 kilonewton force here acting downwards. Its moment about point E will be 3 times 2. Its perpendicular distance being 2 here. And it's tending to rotate in a clockwise direction, and because we've assumed anti-clockwise is positive, that's a negative moment. And then of course we've got the moment generated by the 2 kilonewton force out at the end, and its perpendicular distance will be 2 plus 2 equals 4, and it's a negative moment as well because it's tending to rotate clockwise. Put all of that equal to 0, solve for our unknown reaction force RA. Right, so let's look at some of the forces in the x direction equal 0. We've only got 2, REX and RA. We've just found RA, so we can easily find REX. And then some of the forces in the vertical direction, as I mentioned before, we should be able to see that we can find that pretty easily. We've only got REY as an unknown, and then our 2 known loads. So REY will be 5 kilonewtons. All right, so that's the rigid body equilibrium part of the solution, looking at the entire truss and calculating our reactions at the supports. So let's go to the next page. So I've just copied over my free body diagram here for reference. So you don't have to keep redrawing the free body diagram. I just put it on my next page so I don't have to keep flicking backwards and forwards. All right, so the next thing is to just put underneath there the values that I found on the previous page and start to look at the joints and do our method of joints to analyze the forces in the members of the truss. All right, so I've already said here is to start looking at joint C. Why have I chosen to start with joint C? Because that's the one joint where I have only 2 unknowns. All right, so remember, in using method of joints, we're looking at particle equilibrium for the joint. And if it's particle equilibrium, then we only have 2 equations of equilibrium that we can use. So therefore, the maximum number of unknowns that we can solve for is 2. When we go to look at other joints, such as D and B, we need to use the values that we found at joint C in the free body diagrams of joints D and B, so that then we can find the values of the other unknowns. All right, so let's draw our free body diagram, and because it's a particle equilibrium problem, it's just a dot, and start by putting on our known load. And then, because the trusses are made up of pin connected members, so pinned at each end, therefore all of the members of the truss are 2 force members in equilibrium. So therefore we know that the force acting on each end of the truss member must be directed along the line of the truss. And the forces that we're showing here on our free body diagram of the joint, these are the forces that the truss member exerts on the joint. And equal and opposite to these are the forces that the joint exerts on the truss member. Okay? All right, so now having put on the directions of our forces, we can start to look at the sense of the force in each of our unknowns. Now, if you can't, or if you're unable to do the thought experiment to try and work out which sense these forces need to be in, so which way to put the arrowheads, what I suggest you do is just assume that they're all in tension, they're all positive. And then when you do your free body diagram and write your equations of equilibrium according to the arrowheads on your free body diagram, if the member is in compression, you'll get a negative answer. Okay. Don't then go and change your arrowhead on your free body diagram. Just leave it as it is, and note in your answers that the negative number indicates that member is in compression. All right, so I've put on an arrowhead here for this one, which will be for the member BC up to the right, and that's because I can see this force is acting downwards. I have no other component of force in the vertical direction, so this force has to have a component in the upwards direction. Okay. So this member is going to be in compression because it pushes into the joint. If I drew a free body diagram of the member, so let me just quickly do that. So if that's the member BC, then acting on the truss member at point C will be equal and opposite to what we have on the joint at C. So these two forces here must be equal and opposite. And then at the other end at B, we'll have the force that the joint exerts on the truss member at B, and that of course must be equal and opposite to the one at the other end at C. And then if we go further and look at the joint at B, and we'll do this in the coming pages in the rest of the solution when we need to do a free body diagram of joint B. So we'll have that. So at each connection, we have equal and opposite action-reaction pairs. Okay, so we're obeying Newton's third law at these locations where we've imagined that we've separated the truss member from the pin joint. So we have these forces here, must be shown equal and opposite to each other. And then for our horizontal force here, now in member CD, because our force in member BC is acting to the right, or has a component acting to the right, therefore for this joint to be in equilibrium, this force here in member CD must be to the left. So this one is pulling away from joint C, so therefore if we draw a free body diagram of member CD, right, we must have equal and opposite this on end C of the member CD, so that will be pulling to the right, and at the end D will be pulling to the left, so you should be able to see that that will be in tension. Right? Whereas what I drew before, we could see that the member CB was in compression. Right, so, and as I said, if you can't, or if you have difficulty doing this, just assume all of these forces are in tension. So if you're not sure, just draw the arrowhead of this one acting down to the left. So that would be showing it as in tension. And then when you get a negative answer, that tells you that it's in compression. Right? But don't go back and change the arrowhead, just leave it as it is. All right, let's continue on with the solution. Let's label our unknown forces here. So force in member CB and force in member CD. Angle theta between them. Okay, so I've just worked out the angle in this case, which works out to be 36.87 degrees just from using theta equals, or tan theta equals opposite over adjacent. So then the inverse of that is theta equals the inverse tan of opposite over adjacent. For those sharp-eyed amongst you, you might see that this is actually a 3-4-5 triangle. Right? And you could use those ratios if you want. All right, so sum of the forces in the vertical direction equals 0. So just applying our equations of equilibrium. We have the vertical component of FCB. So this is our angle in here, theta. The opposite side gives us our vertical component, so FCB sine theta minus 2 equals 0. So hopefully by now you're pretty good at doing your trigonometry so that you don't need to be drawing your components all the time and drawing the little triangle all the time. You should be able to just look at the force and be able to work out the vertical and horizontal components. Okay, so rearranging the equation, we can solve for our unknown force FCB. Using our equation of equilibrium for forces in the horizontal direction equals 0, have FCB cos theta. So again, we need the horizontal component of FCB, so the adjacent side to our little angle in here, so FCB cos theta minus FCD. rearrange and solve for FCD. All right, so let's move on to the next joint to analyze. So we can choose joint D or joint B. Which would you choose? I'm going to choose joint D. Do you know why? Because if I go to joint B, I've got one known force, FCB, that I've just calculated, but then 3 unknown forces in the other 3 members that are attached here. Whereas if I go to joint D, I have the force FCD that I've just calculated over here, and my 2 unknowns will be the forces in members ED and BD. Right, so the next one will be joint D, and just notice I put in here whether they're in compression and tension. Right, so here I need to know, in order to put compression and tension here, I need to know what direction the arrows should be to represent tension and compression. If I had just assumed them all in tension, so all pulling away from the joint, then the force in CB would have come out negative. In here, that would have come out negative, and that would have told me it's in compression. Right, but I can see here, right, pushing in on the joint, equal and opposite on the member, pushes in on the end at C and in on the end at B, so therefore that will be in compression. All right, so moving to joint D, start with our known force acting on the point, put in the force directions for the other members. So we know the forces must be acting along the joint members because acting along the members of the truss because they're pin jointed members. And we've just found FCD on the previous free body diagram. So here, what we draw must be equal and opposite to what we had at C. All right, so then we've got 2 unknowns left. We've got forces in ED and BD. So it's pretty easy in this case to work out where to put the arrowhead. The only force we've got acting vertically other than our load here is our force dB, so that one has to be up. And then on the left hand side here, our force in member ED must be acting to the left for this to be in equilibrium. Right. Label those with some labels that we can use in our equation. So let's look at some of the forces in the horizontal direction equals 0. So this is all pretty straightforward. FDE is going to be equal to FCD, which is 2.667 kilonewtons that we found previously, and that's in tension. And from some of the forces in the vertical direction equals 0, FBD will be equal to 3 kilonewtons. And because it's pushing into the joint, that's going to be in compression. All right, so let's go to the next page, and I've just copied over my free body diagram again and the values that we've found so far, and start looking at joint B. Okay, so looking at joint B, draw my free body diagram, just a dot with the forces and their directions along the lines of the members. Here we have our force that we calculated just before, FBC. All right, so here we've got our force FBC acting into the joint, and it must be equal and opposite to what we had on our free body diagram of joint C. FBD we also found was in compression, so that's also pushing into the joint, right? Or the joint pushes back upwards onto the end of the member BD. So now we have our 2 unknowns here, force in member BE and force in member AB. All right, so we can look at our solution here. So how have I got this arrowhead upwards and to the left? If I have forces acting downwards here, so I've got a force acting downwards, the vertical component of this force is acting downwards, then for this to be in equilibrium, this force has to be acting upwards. And because these 2 forces here, this one and this one, are both acting to the left, then my force here, AB, must be to the right. Give them some labels that we can put in our equations of equilibrium. Just noting there our angle again theta that we calculated before, applying our equations of equilibrium. Sum of the forces in the vertical direction equals 0. So we have FBE sine theta. So FBE, vertical component, is the opposite side here. So opposite to the angle theta. So FBE sine theta minus FBD minus the vertical component of FBC, which is again opposite to the angle theta. So therefore sine. We can put all our values that we have from before into that and solve for the force in the member BE, which is 8 1/3 kilonewtons. And that force is pulling away from the joint, so therefore in tension. Now looking at some of the forces in the horizontal direction equals 0. We have FAB minus the horizontal component of FBE, adjacent to our angle, going to the left, so minus FBE cos theta, and similarly minus FBC cos theta equals 0. Put our known values in and solve for our unknown value for FAB. And that's pushing into the joint, so therefore in compression. So if we're now going to look at joint A, so we've got some of the forces already, but we can do this as a check. So FAB we've just calculated, and RA we calculated before as our reaction force, and then we've also got our force here, FAE. And I think you can quickly see before we get to that FAE is going to be 0. But let's deal with the horizontal forces first. So FAB equals RA equals 9.33 kilonewtons. So that checks out with what we had before. And some of the forces in the vertical direction equals 0. This is our only force in the vertical direction, so therefore FAE must be equal to 0. Okay, so that one's a 0 force member. Right, so going to our next page and copying all that across for reference. So we've found all of the forces now, but let's do one last check by analysing joint E. So if I draw a free body diagram, joint E, and put on my reaction forces here and put on some unknowns, or pretend that they're unknown, I guess. We've already calculated them by doing method of joints elsewhere. Right, we also worked out that FAE was equal to 0. So looking at this, FDE must be to the right for equilibrium, and FBE must be acting downwards. So if we do our equations of equilibrium there, we have REX equals FDE to the right plus FBE cos theta. So we get REX equals 9.33 kilonewtons. So what I've done is just to use the values that we calculated through method of joints to confirm that it ends up being equal to our external reaction force. Okay, so that check is okay. Then some of the forces in the vertical direction equal 0. We have REY equal to FBE sine theta. Remembering that we found FAE to be equal to 0. Does that check out with what we had before? So REY from our rigid body equilibrium of the entire truss is 5 kilonewtons. So we get that here in our check, so that's okay as well. So I've just summarised the final answers, rounded up to 3 significant figures, and just indicated on the free body diagram all of our members and whether they're in tension or compression. Right, and if we look at these, hopefully these kind of make sense to you. Right, so you can see this force is pushing down here, this force is pushing back up here, so around this side should be in compression, and around the top here should be in tension. Right, if you got, for example, a compression here, right, you might think, oh, that looks a bit odd. Or if you've got a tension in here but a compression here, you think, well, that doesn't look right. You probably should go back and check your calculations and free body diagrams. Right, so I think that's the end of the method of joints section. Next, we'll go and check our answers by applying the method of sections. Okay, so looking at method of sections, one of the more difficult things that students find when they're starting off with analysing trusses and deciding where to take a section through. The thing to make sure that you do is to not cut through any more than 3 truss members. And also, if you cut through 2, then essentially you're really just doing a method of joints solution rather than a method of sections. Okay, so take a cut through 3 truss members, and then you need to look at one side or the other. Here we've got some loads applied to the right of the cut, so we'll look at that. Okay, so we should be able to apply our 3 equations of equilibrium to work out the forces in each of these 3 members for the section of the truss to the right of our cut. So drawing my free body diagram for that, draw the whole of the right hand side of the cut, and then where we've cut through, just draw your forces along the lines of the truss members, and then we'll think through whether they need to be in tension or compression, or to the left or the right, or up or down. If you find this not so easy, again, what I suggest is just make them all in tension. And then, assuming that you do your equations of equilibrium correctly and your algebra correctly, then your answer, if it comes out negative, will tell you that it's in compression. We need to think about where we're going to take moments about. And usually in taking your cut through the section, you'll have 2 of the members meeting at a joint, and then a third one somewhere else. So if we take moments about point B here, the force from member BE and the force from member AB both pass through point B. So therefore they have 0 moment about point B. So if we write our equation of equilibrium about point B, that will enable us to solve for the force in ED straight away. And we can use that to work out, or that thinking to work out whether this should be to the left or to the right. So if we look at point B, take moments about that, we've got our 2 kilonewton force over here tending to rotate clockwise about point B. So therefore we'll need this force up here at DE to be acting to the left in order to generate an anti-clockwise moment. Right, so we can do that, but firstly I've labelled all of my unknowns with labels that I can use in my equations, and I've put on my arrowhead to indicate the direction or the sense of that force. Right, so now let's look at the others. So we've got force going in this direction and this direction, so we can't immediately tell from horizontal forces which way these are going, but from looking at the vertical forces, we've only got this one with a vertical component, force FBE, plus our 2 applied loads. So therefore FBE must be acting upwards to the left. And now we can see from our horizontal forces that these 2 are acting to the left, so therefore FAB must be acting to the right. And because these forces here, FDE and FBE, are pulling away from the members, these 2 are in tension, and here we've got the force pushing into the member, so therefore FAB is in compression. All right, so let's start applying our equation of equilibrium, and as we discussed, the place to take moments about is point B. And remember that you must indicate on your equations where it is you're taking moments about. So here, this one's going to be pretty simple. But before we do that, let's put some dimensions on our free body diagram. And here, instead of using the angle that we calculated before, I've noted that this is a 3, 4, 5 triangle. Okay, so you've got 1.5 here and 2. So if you multiply this by 2 and this by 2, you get 3 and 4. So therefore this would be 5. So this is a 3, 4, 5 triangle, right? So the length of this member here, CB, will of course be 2.5. Let's do our equation of equilibrium. So we have FDE times its perpendicular distance to B. So that's 1.5 here. And then we have our 2 kilonewton force out here, tending to rotate clockwise about point B at a perpendicular distance of 2. Because it's clockwise, it's negative, whereas our force from FDE was anti-clockwise, so it was positive. All equal to 0. Rearrange the equation and solve for FDE. As I mentioned, that's in tension. Sum of the forces in the vertical direction equals 0. We can find FBE straight away. So using our 3, 4, 5 triangle, the vertical component of FBE will be 3/5 of FBE in the positive direction minus our 2 loads up here. All equal to 0. Rearrange the equation and solve for FBE. And that's in tension. And then sum of the forces in the horizontal direction equals 0. We have FAB to the right minus 4/5 FBE minus FDE, all equal to 0. Rearrange and solve for FAB. All right, so that's how you use the method of sections. I've just done it through one section here. That's all we need to do, really. If we took sections through here, it really becomes a particle equilibrium or method of joints problem. So these answers match the ones that we got previously. So this is a good check for our calculations that we did before. So let's just have a look here. So I said in deciding where to take a cut for our method of sections, I said take a cut through 3 members and then draw your free body diagram. So here we could take a cut this way and still cut through only 3 members. Right, so let's do that and see what happens. So just drawing the free body diagram for this new cut. So I've drawn up to the right of the cut. So now I have force in member DE, force in member F in BD, and force in member BC in my free body diagram. So if we take moments about point D, FDE, FBD, and the 3 kilonewton force all pass through point D, so they have no moment effect. So the 2 kilonewton force here has a clockwise moment, so therefore we need FBC to cause an anti-clockwise moment, so therefore FBC must be acting upwards to the right. And now having got that, we can see FDE must be to the left because FBC is to the right, and looking at FBD here, it's not necessarily obvious whether it should be up or down because we've got forces coming down and a component of force acting upwards. So you could take moments about point C, or imagine you're taking moments about point C, FBC and the 2 kilonewton force pass through point C, as does the force FDE. So the only forces causing moments about point C is 3 kilonewton force acting downwards to cause an anti-clockwise rotation. So therefore we need FBD to be pushing upwards to cause clockwise rotation. So we can put that in. All right, so now we just need to put equations to basically what I've just described. Sum of the moments about point D equals 0. Again, making use of our 3, 4, 5 ratio triangle. We have the vertical component of FBC, which will be 3/5 FBC, times the perpendicular distance to D, which is 2, tending to rotate anti-clockwise, so positive. Then we have the 2 kilonewton force acting 2 meters away from D and tending to cause a clockwise rotation, so therefore that's negative, all equal to 0. Rearrange and solve for FBC. And that confirms that it's in compression. So if we had just assumed that this force here, FBC, was in tension and had it acting downwards to the left, then we would have got a negative number here, right, to show us that it's in compression. Sum of the forces in the horizontal direction equals 0. So we have FDE and the horizontal component of FBC, 4/5 FBC, do your maths, get that force. Sum of the forces in the vertical direction equals 0. FBD plus the vertical component of FBC minus 5 equals 0. Solve for FBD, and we see that we confirm that because our answer is positive here, when we had our force acting into the member, that this is indeed in compression. And all of these answers match those that we had for our previous calculations. And then the rest of the solution is the same as for method of joint. So I'm not going to go through all of that. All right, so that's the end of the problem. Hopefully that was helpful and you have a better insight into how to analyze trusses using both the method of joints and the method of sections, and also how to determine whether the truss members are in compression or tension, or in fact are zero force members. So yeah, that's it for now, and yeah, see you in the next video.